I think we can start. So the first talk on the afternoon is by Krattenthaler from Universität Wien, Vienna. And we talk about exact enumeration of plane partition and rhombus tiling.
Thank you. And thanks to Bertrand and Philippe for organizing this very inspiring meeting and for allowing me to participate. So what I'm going to do here is inspired by the following observation that in these recent papers of, say, Philippe Di Francesco, Paul Saint-Justin, Jan de Heer, Piatov, and partially others, where they try to attack the Razumov-Stroganov conjecture. Everywhere they run across numbers, and sometimes this is even more explicit, that come from plane partitions. And well, plane partitions, as we have seen partially already, as was indicated in Mihai-Ciucu's talks, these are rhombus tilings. So I said to myself that it may be a good idea to give an expository talk on plane partition, the exact enumeration of plane partitions and rhombus tilings. And so this is the picture that we saw in Jan de Heer's talk. And he had some funny acronym for it, and there are many more. And it also seems that people are a little bit confused about that. So I will also try to clarify what all this means. And so to set the scenery, what I will be talking about is very narrow. That I will start with a triangular grid, and I will mark some partial finite region, maybe this one here. And then the question that I'm going to ask and try to answer is how many tilings per unit rhombus is. And by unit rhombus, I hope that this is already clear after Mihai-Ciucu's talk. I mean this. How many tilings by these things, which can have three different orientations, by unit rhombi are there? And so the whole talk will be on this. So this subject was quite active in the past few years, and this is mainly due to this domino list and email list of friends that was created, I think, in the 90s by Jim Prof, and then more specifically by an article in 96 by Jim Prof, where he presented 20 open problems on the enumeration of perfect matchings, and many of these problems addressed enumeration problems for rhombus tilings. And so I am embarrassed to say that I got sucked into this and contributed a lot. But in fact, enumeration of rhombus tilings was already done much earlier before, although people didn't know that they were doing enumeration of rhombus tilings, namely when enumeration of plane partitions was considered. And so this traces back to McMahon around 1900. And so let me make the link to McMahon. So enumeration of plane partitions is the same thing as enumeration of rhombus tilings of a given hexagon. And in order to have a tiling, you have to have special hexagons, namely those where opposite sides have the same length. Thanks. Okay, so here is I admit, not a typical tiling, but this is certainly one. And now, if we introduce colors, then it starts to become three-dimensional. So maybe I take away that one. Okay, that will float. And so what we see here is a pile of cubes in 3 dimensions. And if we insist that the piles, so okay, what property does this pile of cube have? The property that this pile of cube has is that when you start down there and you go in any direction, you never move up. You may stay on the same level, you may go downstairs, but you never move up. So this is the property of this pile of cubes, unit cubes. And if we insist that these piles stay inside a given box, then we have a perfect correspondence between rhombus tilings of the hexagon and these piles of cubes, because there is a unique way to fill in these gaps here. Okay, so we are still not at McMahon. So for McMahon, plane partitions were arrays of numbers. Like this one here. So this area of numbers in fact corresponds to this picture here. And the only thing that you have to do is that you look from very high up in the sky on your pile of cubes. And for each square that you see from very high up, you record the height of the pile of cubes. So this is height 6, height 6, height 6, 5, 4, 3, and then you see these numbers coming up. And then if you want to have a formal definition of a plane partition as in McMahon, then here it is. We forget about the first part. So here is a plane partition. This is an arrangement of integers, non-negative integers in our case, such that when you go along rows, the entries are non-increasing. When you go along columns, the entries are non-increasing. And that's it. This is a plane partition. What I left out there were zeros to fill the box. So the very first problem that McMahon was interested in, if you fix so now I return to the piles of cubes, to the rhombus tiling picture, because I explained rhombus tilings of a hexagon and plane partitions. This is really the same thing. If you fix the surrounding box, how many plane partitions, piles of cubes, how many rhombus tilings of this hexagon are there? And he was able to prove that if you talk about plane partitions which sit in a box with side length A, B, and C, then this is given by this very nice product formula that already showed up in Mihai Ciucu's talk. And because we have this correspondence, it means the number of rhombus tilings of hexagons with side lengths ABC is given. This is just another way to write the same thing. Is given by the same formula. Okay, so that was McMahon, and that was around 1900, and then for a long time, not so much happened on plane partitions, or as we now would better consider them as rhombus tilings of a hexagon. But there was one problem that McMahon left for the world after him that he couldn't solve, which was the problem of enumerating symmetric plane partitions. And now we come to this funny terminology. Wow, funny. So we come now to symmetries of plane partitions. And actually, symmetries of plane partitions are really best explained with rhombus tilings. So what McMahon tried to do was to, after he had found this result, he looked at plane partitions, or in our language rhombus tilings, which are symmetric with respect to reflection along this vertical whatever. In the rhombus tiling picture, it's a vertical line. And you can see that this rhombus tiling is in fact symmetric with respect to this reflection. And he had a conjectured formula, but he was not able to prove it. So as I say, that was left behind. And in the 70s, people started again to work on this, and they discovered that one could also look at other symmetries of this thing, and because such a hexagon could have many other symmetries, for example, 120-degree rotation symmetry. So in the piles of cubes picture, you can simulate that easily, but here it's even more easy. So you rotate by 120 degree. If the plane partition, the rhombus tiling, is the same after rotation, then you say it's cyclically symmetric. And finally, so you must understand that this picture didn't exist. So to discover the missing symmetry in this other picture was more difficult, namely the complementation symmetry. So in the piles of cube picture, it would mean that you consider piles of cubes that is sitting in some box. You take the pile of cubes out, and then something remains. And if you rotate it into the correct position, then it would be again a pile of cubes. There are actually two ways to do it, and depending on how you do it, if a plane partition and its complement are the same thing, then it's called self-complementary, respectively transpose complementary. So self-complementary in this picture means 180-degree rotation. Transpose complementary means reflective symmetry with respect to this axis. And in fact, this one has all these symmetries. So just to summarize, there are these three symmetries, and now you can combine them in all ways. And here is the terminology that was partially already used. So here you can see everything from symmetric, cyclically symmetric, up to transpose complementary, and you can combine these things. And if you do this, then you obtain symmetry classes for these plane partitions, respectively rhombus tilings of a hexagon. And the surprising thing is that for all these 10 symmetry classes, there exists a formula that looks like the formula that we have seen of McMahon. That is a very nice product formula. Why this is so, this is really not understood, but it's simply the case, and all the enumeration formulas have been proved, but there is still one open conjecture which I will not really address in this talk. There's a Q enumeration of totally symmetric plane partitions, and this is still open.
In the sense that the proof is open, but the formula is easy to conjecture.
Yeah, the formula is easy to conjecture. For Q enumerations, it's even easier than for just plain enumerations. But if you have these nice product formulas, this is so easy to guess. Even for just enumeration, there are guessing programs which do it for you. You plug in the first few values and out comes a formula. Okay, so what I will do now is that I give you a parade of results on more results on rhombus tilings, and I will intermingle it with giving some glimpses of what the ideas are, what the ingredients are for the proofs. And really so now I want to be very precise. You remember my title was Exact Enumeration of blah, blah, blah. So I mean exact in the sense of mathematicians, that is exact as opposed to asymptotic, whereas apparently in physics exact is as opposed to approximative. Okay, so when it comes to exact enumeration in the sense that I defined now, then the main ideas that are behind all the results, and actually already when we talk about, say, the 70s, these are the main ideas, although, for example, in the 70s the non-intersecting lattice paths didn't exist, but what people were doing was very often exactly this. So non-intersecting lattice paths, I will mention this. It appeared also in Mihai talk. Then from the lattice paths, there are theorems saying if you want to count such non-intersecting lattice paths, then you get a determinant formula or a Pfaffian formula, depending on the situation that you are in. And then another very powerful thing is Mihai matching factorization theorem that he also mentioned briefly, but didn't explain. That helps very often a lot to simplify. And in the end, you have to compute some determinant, and that's something which I will not address very much here. Those who have in mind that rhombus tilings are the same thing as dimer configurations on an hexagonal lattice may wonder why the Castelline determinants, which appeared in the first talk today, do not play such a big role here. And it's simply the case with two notable exceptions, which are two papers by Kuberberg, at least to my taste. The first one is a paper where he for the first time proved case 9, the transposed complementary, no, maybe the self-complementary cyclically symmetric plane partitions case. And then there's another very interesting paper which is on the enumeration of dimer coverings in graphs with symmetries, where he uses the Castelline determinant and representation theory on the Castelline determinants. But otherwise, it's mostly these things that appear. So if we come back to McMahon, then, and if I now want to explain the non-intersecting lattice paths, then it turns out that McMahon's formula is just a tiny special case of something much more general, namely what you actually can do. So you see this is also a hexagon. 1, 2, 3, 4, 5, 6. But on one side you have these dents, triangular dents. And if you ask, so forget about the symbols. If you ask, so you are given such a region, and if there are tilings and you ask how many are there, there's a very nice formula again. And why is this so? Okay, so here this is because of non-intersecting lattice paths. That may be a little bit small now. So this is the same region. Maybe I take this one. So we have to agree on some starting points of our paths, which I take as the midpoints of the sides of the edges on the lower border of my region. And then I just follow the rhombi. I just cross them always, and thereby at some point I will arrive at the upper side. So I do this everywhere, and thereby I obtain a set of lattice paths. So obviously by the construction they cannot touch each other, and the name that has been coined for this is slightly confusingly non-intersecting lattice paths, but this is the way it is. And so to see better what happens, what I did here is that I rotated the picture a little bit and deformed it. So this path here that you see is now an orthogonal path with horizontal vertical steps, and it corresponds to this one, as I hope you can see. That one here corresponds to the next one, that one corresponds to this one, and so on. So you get such a set of lattice paths. And then, as I already announced, there are theorems for many situations. Our situation is a very simple one, because the starting points of these lattice paths and the end points, they are all fixed. And the question that we are asking is, how many sets of lattice paths are there with these starting points and with these end points? And well, so for this situation, there is this well-known Lindström-Kessel-Viernot formula, which says this number of sets of non-intersecting lattice paths is given by a certain determinant. I will not make this precise here, but in situations where you have just horizontal and vertical steps, the entries will be binomials. So we are talking about a binomial determinant now in this case, and it's really not very difficult to evaluate this determinant, and you get a nice product formula. So I will just in a moment show you that there may be other situations as well. So let me discuss it right now. If you have fixed starting points, but the endpoints may come from a larger set, not fixed, they are not fixed, they may come from a larger set, then the number of families of non-intersecting lattice paths is given by a Pfaffian. This is a theorem of Okada, and in a combinatorial way that was presented by Stambridge, and actually the idea sits already in an integral formula of De Bruijn, which is very important in random matrix theory. And there is also a Pfaffian formula when you have the starting points from some set and the endpoints are from some other set. And this is an even more complicated Pfaffian formula. And both of these are corollaries of a more general thing, namely the minor summation formula due to Ishikawa and Wakayama, which in many situations is a very powerful thing, and it will resurface again during my talk. So just to show an example where you have fixed starting points and varying endpoints. Or maybe I forget something. Do I? I think I forget something. Okay, I forget something. So I wanted to say one little thing about this one here. So actually, this was that the number of rhombus tilings of that region, respectively the number of non-intersecting lattice paths with these starting endpoints has a nice formula that was known in representation theory also. So also there rhombus tilings were enumerated. And this is because these numbers that I didn't explain that. So I put numbers on the horizontal steps, and the numbers are simply the number of the step in the path. So this is a horizontal step, it's the first one, therefore 1, 2, 3, 4, 5. This is a vertical step, doesn't get anything. And this is a horizontal step, which is the 7th step in the path. So same thing here, 1, 2, nothing. This is the 4th step, 6th step, and so on. And now out of the paths you make columns. And what you obtain is known as a semi-standard tableau. That is an array of integers which is left justified, and where the entries along rows are weakly increasing, and the entries along columns are strictly increasing. And these are important objects in the representation theory. These particular ones in the representation theory of SLN. And so McMahon's formula is just a special case of the Weil character formula for SLN.
The structure of the dance is the shape of the tableau?
Yes, the structure of the dance corresponds to the shape of the tableau. Okay, so let me illustrate that you can have fixed starting points and varying endpoints. So if you look at the second case in the symmetry classes, symmetric plane partitions, so symmetric with respect to this vertical axis. So this is somehow similar to what we have seen in Mihailchuku's talk. So if this is symmetric, then I can throw away 1/2. So I do this here. I throw away 1/2. And then we are considering just half of a hexagon, and then in Mihailchuku's terminology, this would be a free boundary with some rhombi sticking out. And if we now again introduce non-intersecting lattice paths, okay, I do this here, then yes, the starting points, okay, so these are the starting points now for me. The starting points, they are fixed, but the endpoints, they can be anywhere on this, in this region. So we are exactly in this situation. And so there you can see the reason why McMahon struggled with this problem. It's a more difficult problem. So, but finally, people discovered this Pfaffian formula. And actually, for this particular problem, the history is a little bit more complicated, but it requires another step to get to something useful. And then one word about a situation where you have varying starting and endpoints. When you consider the totally symmetric plane partitions, that was this case where the Q enumeration is still open. You are in this case, so therefore you can tell it's even more difficult. And actually this Q conjecture for the totally symmetric self-complementary plane partition is, well, how should I phrase this? Should not be so difficult, because we have an expression in terms of a determinant. Namely, when you take this determinant, it's very complicated, but Suichi Okada simplified it, and then it boils down to this. So the only thing you have to prove is that the determinant of the sum of these two matrices, these are Q binomials, is given by this product. But apparently, this is very difficult. Okay, so now we move into the 90s and to these 20 open problems of Jim Propp. And what he had there were problems of enumeration of rhombus tilings which had some defects. So this is very much in the line of the previous talk. And so, for example, one of the problems that he posed was this one here. So actually, just for m equals n, he observed when you take such a hexagon and you concentrate on the rhombus in the middle, in the center, how many rhombus tilings contain this rhombus? And he observed that this was exactly 1/3. So this is a little bit surprising. That 1/3 plays a certain role can be seen from the observation that if you concentrate on some triangle, then which other triangle it chooses for a rhombus, this is just a probability of 1/3. And since this is symmetric, okay, so this is 1/3, but this physical argument would work in an infinite triangular grid, but here you have boundaries. But still, for this one, you observed that it was 1/3. And there are some other ones which I skip. And so with Mihai Ciucu, we were able to prove this conjecture and actually this generalization where you allow more general side lengths. Okay, so this now doesn't belong to the hierarchy of very nice formulas, but it's not so bad. It has this nice product and a factor which is a little bit uglier, but it's just a single sum, so that's not so bad. And by a certain hypergeometric summation, in the case that n equals to m, this sum simplifies and you get this 1/3. And there are several other results along this direction. I'll just show one, namely, in fact, you have a similar type of formula for basically the same situation where you can consider any rhombus, fixed rhombus on the symmetry axis. So at this point, I want to say again a small word on how this is proved. And at this point, what is important is this matching factorization problem. So those who were here 2 weeks ago have seen this picture already, but Mihai Ciucu didn't have much time to say something about it. So let me say something about it. It's a very beautiful theorem which works for any bipartite graph. And the hexagon, so now I use this correspondence between rhombus tilings and dimer coverings, perfect matchings of a hexagonal graph. So you have any bipartite graph. The only property is that there should be a symmetry axis. So the graph should be symmetric with respect to the symmetry axis. These dotted edges, they are also in the graph. And then it says the number of perfect matchings on this graph decomposes into a power of 2. The number of matchings, slightly deformed number of matchings of this upper graph here, and the slightly deformed number of matchings in this lower graph. And how do you get the upper graph and the lower graph? Well, this is indicated here. So there's a certain rule. You label the, so first of all, this is a bipartite graph. So some vertices are in the white vertex class and others are in the black vertex class. And then you label the vertices A, B, A, B, A, B, which you find along the symmetry axis. And then there's this rule, which edges above or below you have to delete. And then there's this final subtle ingredient that the edges on the symmetry axis in this count have to be weighted by 1/2. But otherwise, I have explained the formula. The proof is completely combinatorial. It's a really beautiful result. Why is this an important result? If you have such a symmetric graph, you want the number of rhombus tilings, the number of perfect matchings. Then by this theorem, you decompose the problem into two smaller problems, and very often it happens that to count the perfect matchings of this graph and this graph is much easier than to do it directly on the complete graph. And that was the case for the previous two results that I have shown you. Okay. So one more problem in Jim Prop's list was, so Jim Prop observed that the number of rhombus tilings of a hexagon where you make a monomer hole in the language of this morning is has a nice formula, and that one, I must say, was proved by Okada with some preparations by myself. But later, Mihai Čuka and myself independently observed that actually you can have arbitrarily large holes in the center of a hexagon, and there is a nice formula. So this is a complete product of factorials, basically. The h's are hyperfactorials. So there's a slight subtlety with half integers, but don't. So it's basically hyperfactorials. And so there's this formula. The proof uses again the Lindström-Gessel-Viernot determinant, but in a slightly non-trivial way. Namely, if you do it directly, for example, exactly on this punched hexagon, you couldn't use it directly because there's again this parity coming in. So if the hole has an odd parity, then you can't use it. But you can use it for the even ones, for the even holes, and okay, then you have some determinant, you work hard and you evaluate the determinant. And then in the second step, you show that actually your counting formula is a polynomial in the parameterizing the hole. That works quite easily by non-intersecting lattice paths. I don't think that you can see that this is a polynomial in M, but it is, and therefore it must also be, since we know it's true for all even values, it must also be true for the odd values. Then, okay, if we have this, then what about symmetries? That is, we take now a hexagon and a hole, and okay, are there rhombus tilings which are symmetric with respect to some of these operations? You cannot use all of these operations, and actually in many cases I don't think that there is a nice product formula, but there are some cases, and one case is for cyclically symmetric rhombus tilings. And to those I plan to come back. And in fact, Andrews didn't know at the time, but he proved that the number of cyclically symmetric rhombus tilings is given by a nice product formula. There's another case where there is a nice product formula, which is for cyclically symmetric and symmetric with respect to this vertical line or any other of the lines that you can see. And this is in fact the case that appeared in Jan de Heer's talk. So this is a result that I proved with Mihai Čuka. Okay, I skipped, there's more, but I skipped that. And you have seen the not completely nice formula for this region symmetric tilings with a symmetric hole in the talk before. In fact, this is quite interesting because in this case, if you use non-intersecting lattice paths, then there's another thing which comes in. So this is symmetric, so you would use non-intersecting lattice paths in this way. So what happens here is that you must arrive at these 2 points. So you are in the situation where some ending points may vary along this line here, but these two must be ending points, otherwise it doesn't correspond to a rhombus tiling of this picture. But fortunately, also for this situation there is a Pfaffian formula due to John Stambridge, and okay, so you are down to evaluating some determinant and you do it. So you have seen at least indications of many more nice formulas 2 weeks ago in Mihai Ciucu's talk. So what I want to do in the remainder of the time is to make a closer link to not to the fully packed loop configurations, but to alternating sign matrices. And in order to do this, sure.
In the geometry with the two holes,
Yep.
this shape, there are no configurations which are simultaneously symmetric under the horizontal and vertical axis.
No, no.
Couldn't this be related to the conjecture you were telling me before, that the total number is the product of the two symmetric classes?
No. It is possible. So did I yeah, it is possible. Let me see. Is it still somewhere? No, it is certainly possible. Ah, yeah, okay. So what you would have is that along the symmetry axis, the rhombi are fixed. It must always be horizontal rhombi along the symmetry axis, and then it decomposes again.
Yes.
Okay, so descending plane partitions. That's a really funny object. I don't require to. I don't expect that you read this. So they have a slightly funny shape. Here it's a staircase, and then here it's as in Ferris diagrams, and they have very funny conditions. Just for the fun of it, I have an example, so it satisfies these conditions. So why descending plane partitions? So descending plane partitions were invented by George Andrews, and what he was trying to do was to prove the then conjectured formula for cyclically symmetric plane partitions. Okay, so I remind you, cyclically symmetric plane partitions, these are those plane partitions which are invariant under 120-degree rotation. So if we, on the rhombus tiling, would attack this problem, then we would say, okay, we concentrate on the fundamental region. Right, because everything else is determined. And what George Andrews was doing, he didn't know rhombus tilings, but he was doing exactly the same thing. So from these plane partitions, which were these arrays of integers, he extracted the information that was sort of the fundamental information there. And when he did that, what he ended up with was arrays of integers very much in the same style. Not exactly this, but you just have to add a few, you have to fiddle around a little bit, +2, -2 somewhere, and that's exactly the same thing. And so he followed the idea that putting a parameter is always, not always, but very often helpful. And so introduced a parameter, and now he had a parametric family of objects like this. And if the parameter was 0, he got the descending plane partitions. And actually what he observed was that the number of objects in his generalized families, when you restrict the entries to an upper bound, they were always given by a nice formula. And in the end, he proved this nice formula. And this is connected to this determinant. And so if you hear all this, then you should already be convinced that actually descending plane partitions is nothing than cyclically symmetric rhombus tilings of something. And this is the case. Descending plane partitions are nothing else as cyclically symmetric plane partitions of a hexagon with a triangular hole of size 2. And in fact, these generalized families, they have just a larger hole, and that's everything. So just to very quickly show you how this goes. Here is a rhombus tiling. You restrict to the fundamental region. You introduce lattice paths. You deform these paths, as we have already seen quite a few times. Then you record the heights of the steps, and you are back to where did the plane partition go? Okay, so probably I will not be able to find it in finite time. You need one more assistant. No, I need to control myself better. Okay, so it seems, so this is, if you now put, so in this case, if you read the numbers along paths and put them in rows, then you get exactly this descending plane partitions that I have shown you. Okay, and so I said I want to make the link to alternating sign matrices. Why do I want to make the link? Well, George Andrews, that was just a special case of his theorem, proved that he observed that the number of descending plane partitions where the entries are bounded above by n is exactly the same number as the number of n times n alternating sign matrices. And if you don't yet know what these alternating sign matrices are, then here is again the definitions. It's matrices of 0, 1s, -1s, where 1s and -1s alternate along rows and columns, and all row and column sums are 1. And even more disturbingly, the number of totally symmetric self-complementary plane partitions, these are those which with all symmetries is also given by this formula. So in principle there should be an explanation, but to say it straight, nobody knows an explanation for this. But the closest, so for a combinatorialist, obviously you want to build up a bijection. But you can imagine that building up a bijection, that's not an obvious thing, because on the ones, for example, for totally symmetric self-complementary plane partitions, here's one. And now map it to alternating sign matrices. So you must have some guide. And for this guide, one really has to recommend to go back to the classical papers, 2 papers by Mills, Robbins, and Ramsey. So this is what I will do in the last 10 minutes. Just to recall that we have at least 2 amazing conjectures how descending plane partitions and alternating sign matrices, and how totally symmetric self-complementary plane partitions, so it's a little bit funny here, it's the other way around, and alternating sign matrices should be related. So here is descending plane partitions. So to explain the conjecture, one has to introduce 3 statistics for the descending plane partitions. So we look at descending plane partitions with entries at most n. So these 3 statistics are the number of entries which are equal to the maximum. Then there are special entries. These are entries which satisfy this condition. And then the number of all entries. All these things you can also see in the, can be easily seen in the tiling picture. The number of maximal entries. So you, okay, that was probably also a mistake. You should again concentrate on the fundamental region. The maximal entries are those which you find along here. If this is at maximum height, so there are 3, then the statistics is 3. The special entries are the horizontal rhombi which are in this wedge. This is the symmetric wedge. And the number of all entries, this is essentially all the horizontally oriented rhombi in this fundamental region. So you can read off everything. And then here comes the conjecture. The number of descending plane partitions with k minus 1 entries equal to the maximum, m special entries, p entries altogether is equal to the number of n times n alternating sign matrices, where the 1 in the top row, there's just one 1 in the top row, is in position k. It has m entries equal to minus 1, m minus 1s, and the inversion number, this is a generalization of the usual inversion number for permutation matrices, is equal to p. Okay. So the purpose of this conjecture is that it gives you a hint how to construct a bijection. A proof would also be interesting, but not really interesting, in fact. If you forget about the inversion number, then, okay, the special entries, okay. So I think it's only proved when you forget about these 2 things. But but still, really you want to understand this. And then, okay. It doesn't stop there. what Mills-Robbins-Ramsey also looked at was, so it should relate to alternating sign matrices. And in alternating sign matrices, they already knew that there were symmetry classes which also had nice formulas. So is there a way to see some of the symmetries on the descending plane partitions? And well, they constructed an operation on descending plane partitions, which is an anti-isomorphism on the poset. And the poset basically is that you consider on this fundamental domain and view it as a piles of cubes. And if one pile of cube is contained in the other, then this is the relation. And okay, if you see this picture, there can only be one involution that has this property. The only thing that I can do is that I flip it over. And it must be this because Mills-Robbins-Ramsey in their paper show that there is a unique anti-isomorphism which does it. So this is the one. And there's the corresponding conjecture. It relates in the same way horizontally symmetric descending plane partitions, by which I mean this operation here. That is, if the descending plane, the rhombus tiling stays invariant under this flip, with these statistics is equal to the number of vertically symmetric alternating sign matrices again with these statistics. Okay, so there is 3 minutes left. 5. That will be really fast, no? So they also have something for totally symmetric self-complementary plane partitions. And this is what I will try to explain in the last few minutes. And actually an extension of that conjecture. Okay, so we take a totally symmetric self-complementary plane partition, and well, we know that information is highly redundant here. We restrict to a fundamental region. The totally symmetric self-complementary are the ones which have all possible symmetries. Rotation, all reflections, everything. So the fundamental region looks like this. And now in the fundamental region, you view this again as a pile of cubes, and you read off the heights. Yeah. Which I have done here, hopefully. Yes. So, well, these are the 2 1s, and this is the zeros. And because of the fact that if it wants to be vertically symmetric with respect to this axis also, this corresponds again to your question, because the symmetry axis there also had this property, you must have these rhombi in the tiling, and they impose a bound on whatever happens here. So this cannot grow higher than this bound here. Okay, so these are the bounds, and what you have also seen is that for convenience I have added 1 to all the entries, and therefore I have also to add 1 to the bounds. So in general, totally symmetric self-complementary plane partitions contained in the box of size 2n, the cube of size 2n, correspond to such triangular arrays, such the entries are weakly increasing along rows, weakly decreasing along columns, and they have these bounds. we do well, not as similar, we do also a translation of alternating sign matrices. So here's an alternating sign matrix. What I do here is I take the last row as it is. Then here I take the sum of the last 2 rows, the sum of the last 3 rows, the sum of the last 4 rows, and so on. And by the property of the alternating sign matrices, I will get 1s and zeros, no minus 1s anymore. And what you do now is you record the positions of the ones. So the one in the last row is in the second position. The next to last row, there are ones in the second and fifth position, and so on. And thereby you obtain an array with entries strictly increasing along rows. Here is the general formulation. Weakly increasing along columns, but there's an additional diagonal condition, namely weakly increasing along diagonals from lower left to upper right, and this causes all the troubles. So these objects are also called monotone triangles. And what I do now is that I define a generalization of all that, and I use Zeilberger's terminology. So these are the objects which correspond to the totally symmetric self-complementary plane partitions. These are the objects which correspond to the alternating sign matrices. And I cut certain pieces out. For these objects, I take the first k rows. And for these, I take the first k columns. And I have done something else. Namely, I have changed the upper bounds from 1, 2 up to n, 1, 2 up to n, to m plus 1, m plus 2 up to m plus n. So this is my ingredient to this thing. And the conjecture is the following. It's a very refined conjecture. The number of objects of the first kind with parameters m, n, and k with S maxima in the first row. What is a maximum in the first row? This is an entry in the first row which is equal to its upper bound. And T minima in the last row, well, a minimum in the last row, that would be here somewhere, this is a 1. The minima are the 1s. And this is equal to the number of m and k trapezoids of the second kind, where the role of the maxima and minima are interchanged. And the definition of maxima and minima is again in the same sense. Maxima are entries here, which, if you go diagonally, are equal to their prospective upper bound. And minima are entries in the first column, which are 1. And so it's for sure that this is true. Again, a proof of this conjecture would not be very interesting, but it should guide you to find a bijection between these objects. And as a special case, there would fall out a bijection between the totally symmetric self-complementary plane partitions and the alternating sign matrices. And so I guess I have to stop.
The whole, the triangular whole, it is another statistics that also translates to alternating sign matrices through Wunderlich models. Is that included in? Is that indeed yet another statistic Or is it
No,
included?
for the moment it's not included, but I actually, after your talk, I expect that there would be an extension of the first set of conjectures with the whole also.
So it's not included. You don't think?
No, at the moment this is between descending plane partitions and alternating sign matrices. And descending plane partitions in the rhombus tiling picture are those which have a whole of size 2, period. But actually, your work points to an extension, I would say.
So this case of the whole of size 2, is it so singular that, so this corresponds to this fundamental class defined by Andrews, descending plane partitions, but other sizes don't correspond to previously considered?
Exactly. I think the reason that only this class got a name, the other classes, they don't even have a name in the paper by George Andrews.
They could be considered.
It's just because George Andrews observed, oh, that's the same thing as the number of alternating sign matrices, number of totally symmetric self-complementary plane partitions.
So, again, thank you very much.